Okay, let's go and get started today. Today we're going to talk a little bit. Hold on one second here. Today we're going to cover some stuff in class 9, which was we have a few more operators to cover, and then I want to cover get started on arrays. And arrays will be our first aggregate type that we've looked at in here. In other words, more than one value stored together. All right, let's go and get started. All right, so the first thing is a few operators, bitwise operators, and C language being a kind of mid-level language, a lower level than you might be used to. It has operators allow the manipulation of the underlying bits that our data is stored with. And other languages have these as well. So Python, for example, does have bitwise operators, even though you're not you're dealing with changing an integer object that's more complicated the way it's stored in memory. In C, we can actually change the actual bit patterns in the switches that are representing this, rather than just changing an abstract number in some way. Now, the bitwise operators operate on bits. That makes sense. All right, so the first ones here, the bitwise shift operators, they essentially take some pattern of bits as represented by some integer type or some type here, and then we can shift either to the right or we can shift to the left. And the number on this side is how many bits to shift by. So in other words, if I had a pattern of bits here, let's say it was, from your perspective, 0, 0, 0, 0, 1, 1, 1, 1. So we have that. And then we shift it 1 to the right. Then these all move over one position. So this 0 goes to that position, this one goes there, that one goes there, and the one that was here just goes off the end. So we would go from having that binary pattern 15 to having the binary pattern 7 by shifting one position. Now, one thing to note, that A is not changed. If this is a variable containing a bit pattern, that variable is not affected by the shift operator. But the result of this is as if this were shifted by that many bits. So think of this like kind of like a plus sign. So if you just said like variable x plus 1, that would load the value from x. It would add 1 to it to give you a new result, but it wouldn't change x. If we did plus equal 1, that would change it. But if we just did plus, it would not. So the same thing is true. This is not changing the contents of some variable that's put here. It's just taking their value of that, shifting it by this many, and producing that as a result. And that's true whether we're shifting right or left. Okay, here are a few examples. So here's a 5 shifted left by 1. And even though in the compiler, this 5 is not going to be a character like we have here, not just going to be 8 bits, this is going to be interpreted as probably a long int. And so when we do this shift, there's a lot of leading 0 bits here that we aren't dealing with, that I'm not showing here just to save space. But so 5 shifted left by 1. So there's what 5 looks like. We have a 1 in the 4's place and a 1 in the 1's place. 4 plus 1 is 5. We shift that left by 1. The result of this operation, we basically move that 1, 0, 1 pattern over one position. And now we still have the 1, 0, 1, but we've moved it over 1, so that's 10. And interestingly, before I go on from this example, notice if you take 5 and you shift it left by 1, you get 10. You get double the amount. In old video games, and that's true, no matter what number you have, if you shift it left by one place, you have something that's twice the value it was. If I shift it 2 places, I have something that's 4 times the value that it was. And old video games used to use that as an optimization technique because multiplication was more expensive than shifting. And so they used to write stuff in machine code that would shift left by some number to multiply by some power of 2, essentially. Now with modern processors, not as important. But if you're on something that's resource constrained, that could still be useful, something especially that needs to be fast. All right, now 255 shifted to the right by 3. There's my pattern. We move that pattern over by 3. These 3 get lost. They get pushed off the end. The 3 on the other end get padded with zeros, so we end up with 31. All right, 8 shifted to the left by 10. There's 8. We basically are shifting that over by 10 places, so that's going to move over by 10 bits. So now we have this pattern. So 8 shifted left by 10 is 8,192. and 1 shifted to the left by 15. There's a 1, shifted over by 15. Now we have 15 zeros after that, 32,768. But notice that this shift operator is not changing the bit pattern, it's just moving it over. So in other words, 101, we still have 101. Now there is one thing to note where it can change it, and that's the spaces that are left when we shift to the right, they're padded with 0 bits. Spaces to the left, or I should say spaces to the right when shifting left are padded with 0 bits usually. So in other words, if I'm shifting this direction, shifting to the right, then we end up with that being padded. But there are some compilers that if we have a negative number, a number that would be interpreted as a negative, and the way negative numbers are represented in these bit patterns would be a method called two's complement, where the most significant bit is 1 when it's negative, and then the bit pattern is kind of inverted from what it would be and moved over by 1 since there's no negative 0. But with that two's complement, some compilers on some architectures, if you shift and the most significant bit is a 1, it'll pad it with a 1 rather than a 0. It's only when you're shifting to the right like this. So if this were an assigned character type and that was 1 representing a negative number, shifting to the right may have padded this with 1s instead of 0s. So just note that usually it's the case where it pads with 0s, not necessarily always. So you got to be cautious of that if you're writing platform independent code. Okay, next set of bitwise operators. Let's look, well, the next one, let's look at a bitwise AND. And bitwise AND uses the single ampersand. And essentially what it does is it lines up, imagine the two values being stacked on top of each other with the bits from one below the other. It lines up bit 0 and bit 1 and bit 2 and bit 3 of the two operands. And basically it follows this. It produces a 1 when both operands have a 1. So if I have a 1 stacked on a 1, I get a 1. If I have anything else, I get a 0. And the resulting pattern is that bitwise AND of all the individual bits. Now, keep in mind that there are no borrows or carries or anything like that. All that matters is this table here. So if you look at that table, 1, 1, you get a 1. Anything else, any other combination, you get a 0. And here are some examples, 10 and 2. So here's what 10 looks like, it has an 8 and a 2. And then we're ANDing that with 2. So in other words, the only places, let's start with bit 0 over here, 0, 0. Well, we look at our table, 0, 0 produces 0. The next one, 1. So 1, 1, that produces a 1. But when we get all the way up here, we have a 1 in that position, the bit 3 position, and there's a 0 there, produces a 0. So the only place that it passes that data through to produce a 1 is when both of them have a 1. Here's another example, 255 and 15. Well, these have 0s in the one position and 1 in the other. These ones all have a 1 in both positions, so this passes the 15 through. And then here's one with 1110 or 11110000 and 00011111. So the only place where both of these are 1s is in that position, that 0, 1, 2, 3, 4 position. So that's the only one that ends up with a 1. Now, one interesting thing about this and a really powerful thing about using the bitwise AND is it's used for what's called masking. So in other words, if all I care about is one bit in this pattern, or a set of bits in the pattern, notice that it passes them through. So in other words, when I have a 0, it kills whatever is in this the other one. But if I have a 1, it passes through whatever's in the other one. And that can be really useful. So for example, this top case, 10 ampersand 2, notice here where I'm ANDing with 2. That's a 1 in just that one position. So that's everything's going to be forced to 0 except that one position. And that one position is going to be a 1 when this one's a 1, a 0 when that one's a 1. So this can be useful for isolating certain bits in some sort of larger thing like a register, where you say, all I care about is the low 3 bits, or the low 4 bits. And that's kind of what we did here. We said, all I care about is the low 4 bits. I'll put a 1 in those 4 positions. Everything else will be forced to a 0, and I'll just see what that pattern is that passes through. One quick bug warning here. Do not mix up the single ampersand with the double ampersand. The double ampersand is a logical AND to say if this is true and this is true, then that whole thing is true. The single ampersand is a bitwise AND. And that can be important because a bitwise AND is not the same as a logical AND. Or if you remember back from the previous lecture with the logical AND, basically that says, hey, if this is not 0 and this is not 0, then the result is a 1. Bitwise AND does it by the individual bit patterns, and notice we can get things other than 1 and 0 out of it. We can get these numbers out of it because it's using them individual bits for each of those lined up. All right, next one is bitwise OR. The bitwise OR does exactly the same thing as AND, except it uses a different logic operation. It basically says if one or the other or both is 1, then it outputs a 1. If they're both 0, it outputs a 0. So same thing, stacks them on top of each other, does that. So here's an example, 10 or 4. There's what 10 looks like. There's what 4 looks like. So 10 or 4, we end up with all three of those combined to get 14. It looks kind of like it's doing addition, but it's really not because there are no borrows or carries or anything like that. I guess carries for addition. Now, one thing about bitwise OR is it does something similar to bitwise AND, where bitwise AND can be used to mask bits off by putting a 0 in the thing you're ANDing with something. You're killing those bits, you're forcing them to 0. Bitwise AND will force bits to 1. So notice that this pattern that results was the same as this one, but a 1 forced on in that 0, 1, 2 position right there. So it forced that bit to be on. So OR can be used to mask bits on, and can be used to mask bits off. And another bug warning here, don't mix up, just like with AND, don't mix up the single vertical bar, which is bitwise OR, with the double vertical bar, which is logical OR. And again, with logical OR, all it said, hey, if one is non-zero, or the other one is non-zero, then the output is 1. Otherwise, it's 0. So remember, logical OR only cares about if there's 0 or not, and it always outputs a 0 or a 1. Bitwise OR, though, notice it's doing it on a bit-by-bit basis, just like AND did, and we're getting that. So notice here, we've got that, we OR them together, we get 255. Okay, bitwise XOR. Now, XOR it uses the caret operator, which is the thing that's on the same key as the 6. You press shift and press that, that's the caret. And what XOR does is it does like OR, so it's one or the other, but not both. So what it really does is it's saying, are they the same or are they different? If they're the same, we get a 0. If they're different, I get a 1. And it does it by a bit-by-bit basis. So XOR results in a 1 in any position where the operand's bits are different. So notice here, they're different, we get a 1. They're the same, we get a 0. Now this can actually be really useful for telling if things are match or not without doing like a mathematical comparison. Because if I take something and I XOR it and I get a result of 0, I know that those two things had to be the same. All the bits had to be the same because they matched. And if they didn't match, then the result would be the bit positions where they were different. So here's an example. So 10 caret 4, that's not 10 raised to the 4th. If you're used to other programming languages, you might look at that in code and think of that. This is 10 XORed with 4. So here's the bit pattern for 10. There's a 1 for 4. So we want to say, where are they different and where are they the same? So they're the same there, we get a 0. Same here, get a 0. Same there, get a 0. Same there, get a 0. Different, get a 1. Different, get a 1. Different, get a 1. Same, get a 0. And we end up with this 14 as the output. And here's some other examples for you to look at as well. And XOR has a number of uses. It's actually can be used in like random number generators. We'll not talk about that now, but the bug warning here is different than the other ones. Remember over here we had OR, don't mix up the logic bitwise OR with logical OR. Over here there is no logical XOR. In this case, the thing not to mix up that caret operator with is exponentiation. So if you do 2 raised to the 10th power, there is no exponentiation operator in C, but it'll let you do 2 caret 10, but you're not going to get what you think you're going to get if you think that that's exponentiation. So just be cautious about that. And again, there's the truth table for XOR. Okay, the bitwise not operator basically inverts all of the bits in some operand. So this one is not, this is a unary operator, not a binary one. So we don't have two operands where this and this or this. It's just not the thing that follows. So in this case, we have not 10. 10 looks like that. What's the inverse of that look like? Well, if it's a 0, we flip it to a 1. If it's a 1, we flip it to a 0. And then it evaluates as some number in memory. And here is another bug warning. Don't confuse the tilde. That's the tilde is the bitwise inverse operator. Don't confuse that with the exclamation mark, which is the logical not, which basically says if this thing is not 0, produce a 0. If it's 0, produce a 1. So the logical operators always output just 0 or 1. The bitwise operators do whatever they do to the bit pattern and produce that new bit pattern. Okay, now, just like we mentioned earlier, those operators, none of those operators affect the actual item in the variable. And so you'd have to reassign them back to that. Well, it turns out you can do that with a bitwise modifying assignment operator, just like we had plus equal, minus equal, times equal, mod equal. We also have shift right equal, shift left equal, ampersand equal, or and equal, or equal, and XOR equal. Now, again, don't fall into the trap that using the bitwise operators like A shifted right by B is affecting A. It's producing a result that is what this would be shifted by that, but it's not affecting these. If you want it to affect it, you have to use the modifying assignment operator version of it. Okay, sizeof operator. The sizeof operator, even though this looks like a function call, it's not. This is an operator that's built into C language, and what it does is it gives you the size in bytes of some type, or you can use sizeof on an actual variable of some sort, or an expression of some sort that you could put in there. So if you do the sizeof, and actually you could put parentheses around this too and put a variable inside the parentheses, but the idea is that sizeof says how many bytes of memory, how many 8-bit blocks does this thing take up in memory. And since C is a kind of a systems programming language, an operating systems programming language, that can matter. How many bytes of storage is this thing taking? We need to know to allocate that amount to stick that in there, or we need to know we want to make a copy of this thing. How do we do that? Now, and remember that's in bytes, not in bits. So if I were to do a size of, for example, down here, a float takes 4 bytes of memory, or 32 bits. So we would get that. And if I were to do a size of a double, I would get 8 out of that. If I do a size of a unsigned character, I'll get 1. If I do a size of a short int, I'll get 2. And we're going to see sizeof used later on today as well. But notice that we can also do a size of some variable. So size of ch would produce 1 if that variable is an unsigned character. All right. The conditional operator, sometimes called the ternary operator. And it's called a ternary operator, unlike a binary operator, because it's 3 parts. And it's also got 2 symbols that we use. We use a question mark and we use a colon. And what the ternary operator does is it evaluates kind of like an inline if. In other words, it says, hey, if this expression here before the question mark is true, then evaluate this first part, or as this first part. If this expression here is false, evaluate as the second part. So in other words, it's like an if true, do this, else do that, which you can see it, or else, but it's not really do this, it's more evaluate as this. So if this is true, evaluate as that, else evaluate as that. So think of it kind of like an if statement. So for example, here's the use of the ternary operator here that says, hey, if x is less than y, then evaluate as x. Otherwise, evaluate as y. So in other words, that we did that program before where we were saying which one is the min out of these 3. You could do that with something like a ternary operator like this. So you say whichever one is the smaller of the 2, put that one, pass that one through to z. So this single line like that is the same as if we were to say if x is less than y, then z is equal to x, otherwise z is equal to y. And this can be really concise. The cool thing about that ternary operator, is you can use that inside of other expressions. And you could also use that inside of another ternary operator, for example. So it's a very convenient way to say, hey, in the case that some condition becomes true, evaluate this way, otherwise evaluate this way. So it might be if combat multiplier active, then do this, otherwise use the normal formula for computing the amount of damage done. And that can all be in one line without having some more complex multi-line thing like this. Okay, so now we're on to arrays. And an array, just like an array in other languages, or the meaning of the word array in English, like an array of colors or an antenna array. The antenna array is down. We can't talk to the aliens anymore in a movie. Array means essentially a group of something. So our wide array of colors means you have a whole bunch of different colors. An antenna array means you have a collection of the antennas somewhere. Now, in C language, an array is a block of variable data all stored under one name. And rather than dig into that further right now, let's look at an example. So to declare one, you still use the same type that you're used to. You give it a name, just like any other variable, but you would use tell how many cells you want to be reserved for that. So in other words, this single line here is creating space for 365 integer variables, and all 365 are being stored under this name, daily_temp. And then to access them, we just use the square bracket notation to index them. So daily temp 0 is 30, daily temp 1 is 34, and then the last one, daily temp 364, is 40. Now, one thing to note is that this is another bug warning I probably should have put here, that this is the number of items we want, not the index of the last one, and the indexes start with 0. So the last one in our list is always going to be one less than the total number we reserved here. So this is 365. This is always going to be one less as the last one. And that's going to prove important. And how's that going to prove important? Well, array indexes, since they always start with 1, or always start with 0, the number that you declared for it is always going to be 1 less than the maximum one in the list. But let's just go through these. Arrays are always allocated as a contiguous block of memory. So in other words, over here, how much memory are we taking up? Well, 365 integers. Each one is, on a 32-bit system, 4 bytes. So 365 times 4 is how many total bytes would be, and that's a contiguous block of memory. It's not stored in some opaque, non-understandable fashion by some of it's allocated here and some is over there, and it has all these objects that are all tied together kind of mysteriously behind the scenes. It's actually just a big block of memory. And so arrays are allocated as a contiguous block of memory. The name of an array, when you use it by itself, evaluates as the address of the beginning of that block of memory and data, or in memory. Block of data in memory. I said it backwards. And that square bracket notation that we saw over here is really just a shorthand for arithmetic that happens on the address and then a dereference of that. And because that square bracket notation is just a kind of operation on the address and then get the data that's at that address, there are no bounds checking on array access. So for example, over here, if I tried to access daily_temp 365, that's off the end of this array. The compiler will let that happen because C trusts us, and it will never check bounds. If I were to index negatively, it would move off the front of that array into memory. So in other words, we have this block of data in memory. We could run off the end and get what's off the end, or we could run off the beginning and get what's off the beginning. And the compiler, the language doesn't know any better. It'll let that happen. And that's not while that's can be the source of bugs in your code, it's not really a problem with C, because you remember what it was designed to do. It was designed to make operating systems, and the idea was to trust the programmer. And if they added code to check the index every time, it could slow things down when you, the operating system programmer, should know what you're doing and know not to go off the end of the array. So it trusts us, and it trusts that we know what we're doing. In some cases, that might be bad to trust a programmer. If I were a computer, I certainly wouldn't trust the programmer, knowing some things that I found and some things I've written myself. I certainly wouldn't trust the programmer, but C absolutely does. So if you want to walk off the end of the array, it's like, cool, let's do that. Let's walk off the end of the array. So if you imagine this was something, hold on, the cat is attacking my microphone cord. If you imagine that this was you're on some bridge and you're walking along, and then you get an instruction that says, hey, take one more step off the end of the bridge. C is like, sure, let's do that. Let's walk off the end of the bridge. And one other warning here is there are no bounds checking on array access. And this is so important that I thought it necessary to really emphasize this. That's a source of a lot of security holes in code, is some unbounded array access where somebody writes code and they're filling it into some finite buffer, some data that's coming in, and a hacker or a cracker, whichever one you want to call it, might decide that what if I fill up more, give them data that's bigger than the size of that thing that they allocated, and I walk off the end. Well, the problem with that is off the end of that array is just other memory. And hold on. So off the end of that array is just other memory. And that other memory could be used for storing other variables. It could be code, since code lives in memory. And that's one of the reasons why that's such a big security hole, is you could have a malicious user just stick some random bytes into something off the end of an array, and that could affect the code. It could change how the code runs, and they could inject their own code into that. So be careful. If you have an array where it's up to the user to input data into there, you should bounds check that yourself, but the language isn't going to do that for you. It's up to you to do that if necessary. And where would that be necessary? Anywhere you're accepting data from some outside source where they could put in more data than expected, or any case where you're allowing them to provide you an index into some sort of data. You don't want them to be able to walk you off the end of that array into other memory and then inject other things into there. All right, so let's circle back. We said this earlier, but I want to spend a little more time on this. This whole concept of that square bracket operator for array indexing. And we said this earlier, the square bracket operator, what it really does is just do an arithmetic operation on the address that was given by the name of the array by itself, and then it dereferences that. So in other words, this line of code, array A subscript 2 index 2 equal 4, that's the same thing as if I took this address of A, went 2 positions past that of whatever type this is. So if this was an integer, we'd move 2 integer blocks past that. In other words, we move ahead 4 bytes and then another 4 bytes. So we'd move 8 bytes ahead in memory and then get whatever is pointed to by that, which is going to be that actual block of memory, and set that to a 4. So the square bracket notation has very little to do with actual arrays. It really is just a shorthand for doing this pointer math down here and then a dereference. And that's going to be important to us here in a little bit. Arrays can be initialized when they're declared. So for example, this int b subscript 5, I can say, hey, create that array of 5 integers and set them equal to these values. I could also here make a float array like zoom factors. Like imagine this is for some kind of game and you have like a sniper scope, and when you scroll up it zooms into different levels and out to different levels. So you could list them all in here. So here are the 8 zoom factors here. And again, the indexes here would be 0, 1, 2, 3, 4, 5, 6, 7. The indexes for this one, 0, 1, 2, 3, 4. Again, it's one less. The maximum index is one less than the number we put in there for how many of those we want. Okay, bug warning. Uninitialized arrays are truly uninitialized, which means that they might contain unpredictable garbage. So if you make an array and you don't initialize it, like here's this array of integers, 5 of them, it's not going to be filled with zeros. It's not going to be cleared out. It's going to just be random garbage that happen to be in memory. And again, there's a reason for that, because if you initialized every array when you create it, that takes processor cycles. And C having this very one-to-one relationship with the code to what the processor is actually doing, when you initialize it or when you declare an array and you don't say to initialize it, it says, I trust that you know what you're doing. You're going to do something with it later. So let's not waste the time in the CPU cycles adding mystery black box code to initialize that. But if we initialize it, it will for us. But if we don't, it'll have garbage in there from whatever happened to be in memory from something else that was using that memory or a different program that you ran previously. So just be aware, if you require that to be initialized, initialize it. Kind of continuing along that line is that all uninitialized variables are uninitialized and I don't know what that's. And, all right, will contain unpredictable garbage. So that would include if you just had an int I. What's the value of I? Who knows? Could be 0, might be something else. Could be a negative number, could be just whatever random garbage bit pattern happened to be in that block of 4 bytes or 2 bytes whenever that integer got created. All right, now pointer arithmetic, we talked about that a little bit before when we talked about that square bracket notation. But essentially, the pointer arithmetic, C allows you to do additive and subtractive operations on addresses. And whether those addresses are stored in a pointer variable or an array address, it doesn't matter. If you have something that's a pointer and holding an address value, or you have an address value, you can perform some math on that by adding things and subtracting things. So a pointer arithmetic, though, when you add, for example, 10 like we have down here, it'll automatically account for the size of the type of that pointer. So if this is a floating point pointer, how big are floats? Floats are 4 bytes each. So if I say plus 10, that's going to move me ahead in memory 4 floats. So here's the one I'm on, the one I'm pointing to. I say go ahead 1, that's 4 bytes ahead. Another one, 4 bytes ahead. So when I say plus 10, it's going to move me 40 bytes ahead if this is a float. If that was a character pointer, it would only move me 10 bytes ahead. And that's really a cool feature because it allows us to not have to worry about that. So we can think of this as whatever I'm pointing to now, move 10 of those things ahead in memory. And that can be useful for arrays, as we'll see. Now, you can also subtract them to find how many things apart they are. But again, if this is a float pointer and I subtract 1 from that one, it'll tell me how many units apart are those things in memory based on the size of the type. But in order to do a subtraction between 2 pointers, these have to match the same type. For example, I couldn't take a float pointer and a character pointer and subtract them. The compiler won't allow that because it says, I don't know how many things that is because this is a size of 1 and that's a size of 4. I have no idea which one you want that in terms of. So we have to make sure the types match. Also, increment and decrement work on pointers. This is going to be something we're going to use a lot coming up here in class. But that basically takes a pointer at the address and moves it ahead 1 thing in memory. And remember, plus plus does affect that value. So that actually moves that pointer value variable ahead 1. Plus plus moves it ahead. Plus plus moves it ahead. You can also do minus minus and move backwards 1 in memory. But that allows us to, as we're going to see later on, we're going to be able to look at something and process that, and then do a plus plus on the pointer and move to the next one, and then process that one, and then plus plus on the pointer and process that one. Again, pointers, we said, were a very powerful and useful thing in C. Very much really important to doing anything in C. So we're going to make use of these a lot, the increment and decrement. All right, another concept related to pointers is this concept of what's called the null pointer. And a null pointer is basically a special value that's used to indicate that that pointer is uninitialized or not otherwise valid. And the way that that usually is stored is storing an address of 0 in it. And it's so important that the language kind of defines this all uppercase null for the later standards as a way to indicate a null pointer. And those are used to indicate a pointer that hasn't been set or one that's invalid. And that can be really important because if I just did int pointer PTR, again, I'm making a variable. It doesn't initialize it to 0 automatically. So this is creating a variable with some random garbage value in there that we're going to treat as an address. And then I said, hey, what's at that address? Or change what's at that address. Now I'm looking off in a random place in memory and processing that as if that data that's in that random place in memory is an integer. And if you're in a user mode program, then that's likely to get your program killed by the operating system because it went outside of its allocated memory. And if you've ever had a program that said, this program performed an illegal operation and had to be closed, that's one of the cases where that happened. You have some garbage pointer value, you try to access whatever data is there, the operating system catches you outside of your memory space, trying to get into somebody else's memory space, and rather than putting you in jail, it just kills your program. Now, if you're writing something at the operating system, the kernel level, then that can be catastrophic because you'll be off in a random spot in memory and it'll say, sure, let's change that value in somebody else's program that's running. Or let's change that value in memory that happens to be connected to some piece of hardware. And then your graphics card crashes or your hard drive writes garbage to it. And so one of the ways to make sure that we don't have those, you just initialize them to 0 or a null pointer like that. And they're used to indicate that. And you may have seen errors like that, like null pointer exception. That's what that's talking about, where you tried to access a pointer that was invalid. Okay, now back to arrays. And we're going to make use of some of those concepts that we just went over there. And in this case, we're going to talk about passing arrays to functions. So before we do that, though, I want to talk about storing array addresses and pointers. That an array name, when used by itself, you're going to hear me say this a lot over the next few lectures, an array name in C, when used by itself, evaluates as the address of the beginning of that block of memory. So that means if we can get that address, we have a variable type, a data type that can hold addresses of things. That's what pointers are. So I could store that address in that pointer. So here's some example code. I have an integer pointer called PTR. I have an integer array called A that has 5 elements. There they are. I can say PTR equal A because A, there's the name of the array used by itself, evaluates as the address of the beginning of this block of memory. This is going to be 20 bytes because it's 5 times 4 each. Or it could be 10 bytes if this is a short int on a different platform. But this PTR equal A that we have there, that's the same as saying PTR equal the address of A subscript 0. So we could have said it this way. This would have worked too, but so we have to we're doing a dereference and then a reference. This one, we have the address directly. We can do that. Now that I have that in that pointer, notice I can use that square bracket notation to access it just like I accessed array sub 0 because I have that same address. So this PTR value is going to fetch the address, which is the same as where A is in memory, and then it's going to do this operation. So this would have the same result if I just put A here. A sub 0, A sub 4, A sub 5. Now, here's a bug. A sub 5, we don't have an A sub 5. We've got 0, 1, 2, 3, 4, so that's off the end of the array. So this could cause our program to crash, or it could just be some random garbage value off the end of this array. It could be some other data that's in memory after that block. We don't really know, but this is definitely bad because we went off the end. We shouldn't do that. So notice that because that square bracket notation just takes an address, does some pointer arithmetic on it, and then does a dereference, we can do that whether there's a pointer here or whether there's the array name there. And that's going to be the key for how we're going to pass arrays to functions. We can access that array through a pointer to that array, which is what we're doing here. Okay. So while an array name by itself evaluates as a pointer to or the address of, here I'm going to clean up this language just a little bit. Okay, so while an array name by itself evaluates as a pointer to or address of the 0th element of that array, it can't be modified like a pointer value. And this is important to note the difference. So they behave the same when they use the square bracket notation. But notice in this case, I have integer pointer PTR. I have this integer array A that has 5 elements in it, 5 integers in it. PTR equal A, I can do that. I could say that's going to point me to, that's going to make this pointer value hold the address of where this 5 lives in memory. And if I said PTR plus plus, it's going to move it ahead 1. So now it has the address of that 4. And if I did plus plus again, I would move to the next one where the 3 is. If I did plus plus again, I would move to the 2. And plus plus again, I would move to 1. And plus plus again would move me off the end, which C would let us do that. We shouldn't do that, but it will. But notice that I cannot say A plus plus, because A is a place in memory. It lives where it lives. We can't magically make that block of data move ahead 1 thing because it is where it is in memory. So an example here, the analogy that I would like to use is that imagine a pointer variable is like a piece of paper that you're writing an address on. So PTR, you can think of that like a, I don't think I have any post-it notes handy, but imagine it's like a post-it note that you write an address of the university, 940 2nd Street. Now, if I wanted to look at that, I could look at that piece of paper and say, hey, let's go to the next address and scratch that out and be like 941 2nd Street. You could do that, but you could not make the university magically pick itself up and move over 1 address and plop itself back down. So you cannot move the array. You can't change that address, but you can change the address that a pointer variable is holding inside it. All right, now let's get back to how to pass arrays to a function. And all of this is kind of leading up to that. So probably the best way to do this is look at an example. All right, so here's an example. We have this array of 5 elements, and then we have a function that we created called sum that's going to add up the things in this array. And notice we're not really doing anything with that value. Maybe we should. Here, let me add this so it actually does something useful with it. If you want to try this, you can. So I'm going to do print f total. And let's use a integer \n. And then we're going to call this sum function that we're going to create. All right, that's a little better. So now you can actually run this and see it produce the sum of this. So we're going to call this sum function here. What? Here. I want to separate this out to make it a little more clear. What? Nope, I don't want to call it sum. Actually, I've now sum used twice. Let's call this total. Sorry about the live coding. Okay. And let me take that space out there so I can move this down 1 line and make it a little more clear. All right, good enough. So back at it. All right, so we have this integer variable called total. We have this integer array with 5 elements called A. And we're going to call this sum function that we're going to write down here. And we're going to pass to it A, which is the address of the beginning of this block of data, and 5 as how many things are in that array. So we're going to say, hey, here's this pointer to the beginning of this block of data, and there are 5 things in it. Now that function, when we call it, it needs something that can catch or hold an address, because A by itself is the address of the array. So here we are with this integer. We need something that will catch that address and hold it. Well, what kind of variable holds an address? A pointer variable. And what type was this array? Integer, so we make an integer pointer to hold that. So this is now a type that can hold the address of integer data. We pass that in, and there it is there. And then we also need an integer to capture the number of elements of the array. And now we basically just say, make this local variable. We're going to call it sum here. And we're going to add up all of the things inside of there. And we're going to say sum plus equal that. And let me make one more change to take this out and not call this sum. Let's call this local sum. So we don't get confused with the sum name of the function. So notice this local sum, we started at 0. We go through from 0 with I, and I don't have that variable declared either. I need to do that. I need to do that too. I'm going to have to, I'll clean this up here in just a second. What? Don't capitalize that automatically. All right, there we go. Okay, so what this does is adds all of them up, and then it returns that local sum value that started at 0, accumulated the values of all of the ones inside of there. But notice here, even though this was a pointer, I can still treat it as if it were an array. Because this square bracket notation, the indexing, is really just a shorthand for some pointer arithmetic and a dereference. And so it doesn't care if it got this address from a pointer variable or directly from the array name used by itself. It can do that. Okay. Oh, what? All right, hold on. I got to move ahead to where we were. Okay, so here we are here, and let me see if I can fix this so it matches. I don't know why it just keeps changing the size of this stuff. Okay, and let me shift this around. So the name of the array, when used by itself there, and here, it's going to okay, so now we have the same code on both of these pages. Notice in this case, we've got the A being passed into the function. That's the evaluating as the address of where in memory this thing begins. That address then gets plopped into this variable that's designed to hold addresses of integers because it's a pointer variable. But now once we're inside the function, we can access it just using that pointer as if it were a locally declared array. Okay, so a few final thoughts here on what we've talked about today. That everything in C is passed by value. So when we pass, if we want to pass an array, then we have to explicitly make sure we're passing in an address, which with arrays, the name of the variable or the array by itself evaluates as an address. You could also have said ampersand A subscript 0, that would work. And the pointer then can use the square brackets to index that just like it was an array. There's one difference that we'll see in a second. Since arrays evaluate as addresses and pointers hold addresses, they're closely linked in C, which is why we can use that square bracket operator, the index operator, on both of them. Because it says, here's an address, use a square bracket operation, use the type of the array, do the pointer arithmetic, get the think data that's there. If I have a pointer value, it's an integer pointer, and we use a square bracket, it says take the address out of that, jump ahead by this number of places in memory, get the data that's there. It does the same thing whether that address comes from inside of a pointer variable or from the name of an array used by itself. Now there is one difference when using pointers and arrays though, or between the pointers and arrays, and that other than that you can move one, you can change the value of a pointer, you can't move the array, but there's another one, and that is the sizeof. So the sizeof operator gives the number of bytes that are associated with the item or allocated to that item that we store there. So in this case, notice there's going to be a difference here. So let's take a look at this code down here. So we have a long int, and I've made this long just so we don't have to worry about architectural differences. Longs are always 4 bytes each. So long int array A subscript 5. So it's going to make 5 long integers, or space for 5 long integers. It's going to put 5, 4, 3, 2, 1 inside of those 5. And now we have a long int pointer P equal A. That's something we can do. We're taking the address of that array and we're making this pointer hold that same address. So this pointer is now pointing at or holding the address of this 5 in memory. And now we could index both of those, either using A or P, to get all of the contents of that array. It would work identically. But there is a difference. If I say size of A, well, A is an array of 5 things that are 4 each. That's going to give me 20. But if I say, what's the size of P? Well, P is just big enough to hold an address. It's going to give me the size of that address, which depends on the architecture. It could be, if we're on a 64-bit machine, that could be 8. If we're on a 32-bit machine, it could be 4. If we're on a 16-bit architecture, it could be 2. And then if we're using an old DOS compiler, it could depend on the memory model that was used. There's some other things that go into that. But note that this, even though these can be treated interchangeably with a square bracket notation because they're both holding the same address, the allocation associated with each of them, this is 5 units of 4 bytes each, making it 20. This one is the size of whatever that address, the big enough to hold an address. So what gets printed? When I did this on my machine, it's a 64-bit compiler, I got 20 for that, and I only got 8 for that, even though they can be used interchangeably. And that size of the pointer is going to depend on the architecture. Is it a 16-bit, 32-bit, 64-bit? That's what's going to determine that. So one of the things I would encourage you to do is go back to those examples and compile them and run them. You can use that online compiler if you don't want to make a whole project for it and try it. And remember, the way to find that is, and I would try some of this code as well. Again, if you're going to try this, make sure to put a main around it and use it. There's one other thing that I left off of this thing here that we should do to get into good practice. Again, a function before it gets called should have a prototype, should have a function prototype. And I left it off here just to save space to get the concept across. And what a function prototype would look like for this code. Well, here, let's just copy this code into online GDB and switch over to that, and I'll show you, show you what I'm talking about here. So let me highlight this. Also notice that the stupid word processor changes my quotation marks. So when we paste this in, we're going to have to change those quotes because it uses a different open and close quote. Even if I say set the style to code, it'll still do that. So it's kind of stupid. But let's switch over to online GDB real quick here. And you can find this really easily if you just Google search for online C compiler. You'll find this. Oh, you can't see that right now. Hold on, let me move it where we can see it so we can do this together. Okay, so here's my online GDB online C compiler. So there's my code, and I should be able to paste in that code that I just had a second ago. Actually, let's just highlight this. Let's paste that in. And it messed up my formatting, but that's okay. C language doesn't care about that. Let's clean this up a little bit, I guess. And so we don't get a warning about main not returning something. We'll just return a 0 from that. And we got to fix our quotation marks here. And for some reason, this whole thing here went away. I don't know where that went. This should be total. Did I mess up that code? Yeah, I did. I never finished it. I'll go back and finish that before I post it. All right, so let's go ahead and take a look at this. Now, one of the things, if notice we're calling sum here. We don't have it, and as the compiler reads this, it's going to encounter that, and it's not going to know what that is. So if I go and compile this, you'll notice I got a warning. It says, warning, implicit declaration of function sum. That means that the compiler wasn't sure what sum looked like, so it kind of went ahead and generated some code for it, but it kind of did it based on how we used it, and it may have guessed wrong. So the way that we should fix that is by making sure we have a function prototype. And the function prototypes need to be before the function gets used. So up there, and they basically just look like that line and the thing. And actually, let me show you that when I run this again, it'll still work, but now I don't have the warning of the implicit function. Now, it worked there. We got the same result, 15. We got 15 in both cases, which is what 5 plus 4 plus 3 plus 2 plus 1 is. But if the compiler guessed wrong based on what we put in here, the types we put in, it could make the program not work right. So we should always have function prototypes. And the function prototypes, you really can just say, think of it as you take this line, it's the initial line of the function, and just put that in, but we'll put a semicolon at the end. And that's what that's telling the compiler is there's going to be a sum function that's going to return an integer and accept two parameters, an integer pointer and a number of elements. And that's essentially what you should do with every function. It should have a prototype. And if we wanted to move this function into a library or its own file, we could make a header file that has this in it, the .c file that has that in it, and then compile that and make it part of our project. But also notice that this, all it cares about is the return type and the number of parameters and their types. Really, this would work just the same way as if I took these things off. It just needs to know that. That will still work. But it's usually good to leave those on because they give you an indication of what those parameters are used for. Okay, so I'll go back and fix that code. Total, oops. I gotta fix it in two places, so let me go ahead and do that. I just need to put total here. And I need to do the same thing on the next page. Okay, there we go. All right, so what I want you to, let's finish this off again. So what I want you to do is take a look at those bitwise operators. Make sure you understand bit shifting, shift left, shift right, bitwise and, bitwise or, bitwise XOR, the bitwise complement, and make sure you understand arrays and how to pass those to functions, because we're going to have another quiz on that stuff coming up. So we'll stop there. We are at about the 1 hour mark, which is longer than I wanted to be today. But that should give you some time to take the quiz and do the other stuff that you need to do also. All right, so everybody stay safe, and I'll see you soon. And there's going to be a quiz. We will have another lab coming up as well, but let's go and stop where we are now.